And good afternoon and welcome all the participants from NESAC. So, and I really thank sir for the opportunity and also the brief introduction that sir has given on the activities that we have been doing in the domain of lightning physics and early warning. So what we have done today, today's talk, we have prepared two presentations. One will be delivered by Dr. Rekha Gogoi and another by Dr. Abhay Srivastava. So Dr. Rekha Gogoi is actually working in the field of numerical weather prediction since 2010, and she has very good expertise in this domain. So because what we saw from your program that there are already presentations from IMD and NARL, NRSC. So we thought there is no point of saying too much on the lightning basics. So we thought the students may be a little bit of interested on the modeling aspect also. So we have kept a presentation on the numerical weather prediction, focusing on the extreme weather and also lightning a little bit. So Rekha Gogoi will be taking that lecture. She will be basically telling about the model that we are using for the lightning early warning system also. Because I'm happy to share that NESAC was one of the center who was the first in India to assimilate the lightning data into the WRF model. So that experience to some extent Dr. Varali will be sharing, and this will be followed by another presentation by Dr. Abhay Srivastava. So we will be telling a little bit on the instrumentation and different instruments that are in use and the data from which are used for the early warning systems. So definitely, I'm sure both the presentations will be of interest and use to all of the participants. And I think we'll take the questions at the end of the presentation. Each presentation, probably after Dr. Rekha Varali's presentation, we can take questions related to her, because in that case, she'll be able to leave in case she has other works. And Abhay Srivastav's after his presentation. So with this, I request a first presentation by Dr. Gogoi. Over to you, Rekha.
Okay, thank you, sir. I'm sharing my slide. Okay, I think host disable the participant screen sharing.
I will just make you co-host so that I have made you co-host.
Okay, sir.
I have also made Dr. Abhay Srivastava co-host.
So my slides are visible, sir?
Yeah, it's visible.
Hello, everyone. I'm Dr. Rekha Gogoi. As Kundu sir has already mentioned, I have been working in numerical weather prediction for the northeastern region at NESAC since 2010. However, my journey has started from the project called the Flood Early Warning System. Before going to lightning, I just want to give a brief background why we are doing and why it's so important to do the numerical weather prediction. Otherwise, for flood forecasting, you will get water level data from the rivers and all. Then why need to go for this weather predictions part? Because this flood are, if I talk about flood, these are not only like riverine flood. These are flash flood also. Sometimes if our basins are small, then is like 1 hour rainfall also it creates flood. So in that case, our only river level data is not efficient or helpful. Therefore, National Water Policy in 2012 only, they have decided or they have suggested that instead of only going for water level data, we should go for weather prediction or early warning. And we have also started the early warning under the flood early warning system, where we give the high resolution rainfall data. To give a brief background, means how this numerical weather prediction is evolving. Like it is like 1904 only, Jarkins, he has given the concept that numerical weather prediction is possible, because this weather prediction is nothing but your initial value problem. If we know the initial conditions of the atmosphere, then in the next time step, suppose 1 hour, 6 hour, or 24 hours, or maybe 3-5 days, what will happen, that can be using some initial value problem, we can forecast that. So Zarkins in 1904 only, he found that it is possible. But like Richardson in 1913, it almost took more than 9 years to implement it. And he found a model, and unluckily the model did not work. And for his 6-hour forecast, it took a like 6 weeks time for the prediction, because our models are time means it takes lots of time because the models involves lots of observations, data, computation. So what Richardson thought, he wrote a book in 1922, and he thought like someday people will sit like this, and number of people will sit like this and will run a numerical weather prediction model, because at that time this high-end computation concept was not there. But in 1947, you see, like 1913 to 1947, we have the background, like we will do, means weather prediction is possible, but it could not be materialized because your computation, that computational facility was not available at that time, or it may not be thought of. But thanks to von Neumann in 1948, that ENIAC supercomputer or whatever computer is said, it is developed. And then these three genius fellow like Charney, von Neumann, George Wolf, they together create the history and made the first numerical weather prediction model. Why I'm saying that? Because anyone may say like weather prediction, why not using a simple computer you can do? Because it's very difficult to make your administration understand, like for running a model, it's not like a simple computer job. You need a whole lot of computational facility, and it was already faced by our own historians. Because numerical weather prediction models, it involves mainly the governing equations like that governs our atmosphere. You can say about wind forecast equation, continuity equation, temperature forecast. So these equations are already there. Then our job is to how we can fetch the information, the observations. For example, for wind, what are the information you need? Then for running the continuity equations, then temperature forecast equation. So all those things you need basically the observations like wind, temperature, humidity, pressure, some of the basic information you need about the atmosphere, and then you can run your model so that how the model will evolve, that you can predict. However, your model does not know calculation, your computer doesn't know calculations like differentiation, integration. It only knows arithmetic operations. So other methodologies like finite difference method, all those method has been developed, and then these equations are solved using the computational facility. So what a numerical weather prediction do? It does, like it takes care of the equations that govern our atmosphere, then convert them to a form that our computer can understand, and then solve the equations in such a way that you get a forecast like this. So whatever data we feed into the model, it will go to the equation, but your model will convert your equations in such a simpler format that your computer understand that. And finally the model evolve and we get the forecast, like 1 day forecast, 2 day forecast, whatever you need. However, for that you need a very high computational facility. For research purpose, it is okay, like for a 10 or 20 core machine you can start, but for operational forecast, this is the need. Without a supercomputer, it's very difficult to go for an operational forecast because it involves a lot of factors. When you talk about a model, you talk about the surface observation, you talk about the resolution, you talk about the model schemes, parameterization scheme, means what it is, I'm coming back to it, like all those whole lot of thing is happening inside the model, because using those simple parameters on like wind, temperature, humidity, the model, it integrates in such a way that it represents the atmosphere in the next 24 hours. For that, it needs a lot of computational facility. But although we know that so much of computational facility is involved, but still we are doing the weather forecasting, and it is the need, because weather forecasting, it supports the decision makers, because during the emergency and like any disaster mitigation part, early warning plays a very important role. Nowadays, if you see, IMD's cyclone forecast is so accurate that now casualties are almost nil, at least death is almost nil, because the forecasts are to that extent improved. However, when we come to forecast our northeastern region, because why I'm saying northeastern region, because it's a hilly terrain, like 2/3 of the region is covered by hills. So while we run a model here, we cannot run the model at a very coarser resolution, say 27 kilometer or 9 kilometer. We should go nearly about 3 to 1 kilometer. So for that, we need a lot of computational facility observations, because your atmosphere, it used to change, and because of the climatological effect also, your weather conditions are changing. So for model to understand those conditions, you have to give the real-time informations. And if that observations I'm talking about, for running a model, the observations comes from different sources. For example, your automated weather stations, from there you will get information on wind, temperature, humidity, then pressure, and then our upper air observations like balloon data you have, where you vertical layers of atmosphere, you get information, the different parameters, as I have already told, like temperature, humidity, pressure. So not only that, then from satellite we get those informations, all the atmospheric. Then over the oceans we have views, from there also we get upper air observations. Then from aircraft we get observation about the atmosphere. So n number of sources are there, and finally those sources are coming to a common platform, and that is some global forecast system, we can say. Globally those observations are collected in a complete common platform, and those collected data are then converted into some format, because in the beginning only I have said like numerical weather prediction models are initial and boundary value problem. So for initiation of the model you need the observations, and for running that initial conditions comes from the global model, because what we run here is a regional model, and what we get, the data we are using from a global model, and those data finally it goes to the model, and our models are in such a way configured like it has good it should have good horizontal resolution, then it should have good vertical resolution, such that your atmospheric conditions need to be represented well with the available observations. And when we talk about a model, the two main things in a model is the dynamics of the model and the physics. Dynamics, the equations that represents or govern our atmosphere, it is taken care of by that. The dynamic model take care of that governing equation of the atmospheres that I have already mentioned. But the physics, like these small processes, what is happening inside, like the long wave radiation is going away, then short wave radiation is coming back, then cloud scattering, then evapotranspiration. There are small things are happening within the atmosphere, but the model could not take care of each and every effect, because these are based on some equations, and when we set up some equations they also have their own drawbacks, because while we run a model, those equations need to converge, and they need to run in such a way that it won't take much time, because time is the most crucial thing when we go for any early warning or forecast. So if you take lots of time for running your model by explicitly resolving all those processes that is happening in the atmosphere, then the forecast that we are giving will be of no use, because minimum like 5 to 6 hours lead time at least we need to give. So that is why the model, for simplification, it represents the processes that is happening, like the convection it is happening, cloud and precipitation formation happening. So model explicitly does not predict all these things, but it is representing whatever atmospheric processes are happening based on the data that we are providing. So while you run a model, you need to take care of all those things, because any global model or any regional model that is globally available, they will be equipped with many schemes available in the model, but the schemes you will have to choose in such a way that represent the atmospheric condition of your region. So these conditions are very much site specific, so you just can't blindly go use a model and run for your region. There I already mentioned like why parameterization scheme, all those things are so important, the data, because when we develop a model, when we run a model, the model itself has lots of errors involved with it, because models are nothing but a stack of or combination of some equations, mathematical equations. Then mathematical equations, differential mathematical equation, they have their own drawbacks, like not drawback, I will not say, like round of error they will have to take care of. Then your model should converge. So all those things, how we can take care of, then those errors are mainly based on the initial condition uncertainty, then the resolution that you are using, then the nonlinear dynamics of the atmosphere and the ocean. So lots of issues are there with the model, whether you call from the initial condition also, you will have the model error, then from model uncertainty itself, because the parameterization schemes, resolutions, all those things. So that's why we need to go for such a way that your error should be reduced, because your final agenda is to get as accurate as possible your forecast. So that is why you need to reduce your error to a large extent. So if you see this graph here, the first you see this graph's persistence, in the sense means what is happening, it is continuing. If we thought like yesterday what happened, today also it will happen, in terms of weather prediction, then it will definitely not happen. So as time passes, the errors will increase. So this is the forecast model, that is a deterministic forecast model. Ensemble means instead of using a single forecast, we are using multiple forecasts. And then, so if you see, the errors are reducing if we go for ensembles. And finally, if we add some value additions, like from remote sensing based observations we improve the model, then our errors further decreases. However, this spike, if you see in both the ensemble and the forecast models, this spike is always there, and that this is called the spin-up error. Every model needs a time to stabilize itself, because at 00 UTC, if we give a information about what is happening now, the model does not know anything what prior to 00 UTC happening. Is there any instability in the atmosphere? Because it has only the information about the 00 UTC. So when it propagates, so first it will create some issue. Like for stabilization, it takes some time. That 0 to 6 hour we call as a spin-up issue. So if you anytime go for running a model, then you can check that your 0 to 6 hour forecast will be not good. But for flood forecasting, we are getting accumulated 24 hour or like 1 hour, although 1 hourly forecast, but accumulated we are considering. So we are not getting much problem with it. But when you go for high resolution model, forecast for thunderstorm or lightning, you will have to take care of this feature also, like how to get rid of this spin-up problem. And this I already says, like the equations used in the model, they cannot fully capture the atmosphere. Then the model resolution may not be sufficient to capture all the features in the atmosphere. And sometimes the initial observations are not available at every point in the atmosphere, because when we talk about observations are scattered. Like AWS stations, you won't get a systematic spread of AWS stations over the northeastern region. If you talk about upper air observations, you will not get a systematic network of such observations. So you will get some scattered observations. So that means your observations are not like uniformly defined or distributed. And that is why when you run a model, some of the areas where there is no observations, then it will create some biases. So that is why your errors are also coming from the observations. If you see this methodology, like there is one model called MM5 model, this model, what this graph is showing, for numerical integration, this model uses leapfrog second order centered finite difference method. As I have already told, your computer doesn't know differentiation calculation, so it will use some finite difference method and integrate the differential equations. So for the sake of reducing the complexity or time consumption, this model uses a second order centered method, finite differencing method. But what happened, like this is the reality and this is the simulation. You see the differences in the what is reality and what it is. So in time or space, there are deviations because we are compromising while running the model to reduce the time consumption or complexity of the model. We are not using a higher order finite difference method. Instead, we are using some lower order method, and that is why we are getting the error. So the errors are also coming from the numerical method. But another method called WRF, for that same numerical integration, it uses the sixth order centered method. So that is another finite difference method, and you see how your forecast is improving. Why I am showing all these things, although you may not be from the mathematics background or this, but the thing is, like when someone will, like a numerical prediction person, make you understand, like these are the problem we are facing, like these are the computation, you should understand from their point of view also. Because while we run a numerical weather prediction model, we should need to take care of the numerical errors also involved with it. And while instead of using this second order to sixth order, the computation also increases threefold. So that is why we need very sophisticated computational system for running regional models. And then errors in physical processes, because I already mentioned the physical processes, those are happening like radiation budget or microphysics that is involved for cloud formations, then land surface interaction. All those processes are not explicitly, model cannot predict explicitly these processes or represent these processes. It's just mimicking the thing. Like if heat, moisture, momentum transport is happening, then it is just from the observation information it is getting, it is mimicking that, okay, if this is the current condition of atmosphere, this is the wind, this is the temperature, then this will be the heat and moisture transport. It cannot say explicitly, yes, this much heat and moisture transport is happening. So this representation also creates problem. And if you see our terrain, when this is, for example, this is the actual terrain and this is the model representation. So while using a model, the model smooth out the areas. So instead of representing the mountains, the peaks, the undulations, it smooth out. And because of that, when a system or front is moving, then it will just move over it flawlessly. There is no interruption here. But in reality, this is happening. So that is why your representation of the surface variables are also very, very important. Like when you talk about a numerical weather prediction model, it is not only the meteorological parameter that concerns you. It also the surface variables that should concern you, because your surface is finally interacting with your atmosphere. How your wind is moving, all those are interacted by your terrain conditions. So that is why while selecting a model, while using a model, we need to take care of the surface variables also. And for example, for representation of any mountainous a mountain, suppose a model needs minimum 5 grid points. Therefore, the grid size should be sufficiently high that it accommodate all small information that is there in the atmosphere or in the surface. And also, when you consider the vertical, because not only the horizontal, you also need to take care of the vertical layers. Means your model, how many vertical layers should be there that it can accommodate all the atmospheric information, because the interaction at the surface and the atmosphere is higher near the surface. So your atmospheric layer should be more dense near the atmosphere, near the surface. And while you go up, your atmospheric layer can be far apart, because they don't need that much of layer. So those things also you need to take care of. Then finally comes your errors in the initial conditions. When you talk about the errors in the initial conditions, that means whatever observations we are feeding to the model, that is the global model, those observations may have some errors, or maybe those observations are not sufficient to represent your atmospheric conditions. So in that case, what we can do, we can feed the model with our own observations, like your in situ measurements from AWS stations, satellite data, radar, then lightning data. So all those local information you can feed into the model, and whatever global initial condition you take, those information you can correct. And that methodology is called the data assimilation. Actually, here we are actually correcting the global forecast system data that we use for running a regional model. And for data assimilation also, we get data from various sources like satellites, radar, then weather observations, like I have already mentioned, AWS stations, then your upper air observations, aeroplane view. So whatever data we use for generating the initial condition for running a model, for assimilation also we are getting the data from the same source. But in assimilation, we have our own source of data. For example, India have their own meteorological satellite, like INSAT 3D, 3DR, 3DS. So all those data, whichever not there in the initial condition of the global model, we can feed those information into the model, so that further the initial condition can be improved and the accuracy of the model can be further improved. There are different kind of models available. It's up to you which suit your need. Like, for example, the global models. These global models, there are a number of global models available. However, for your regional forecast or your localized forecast, like if you want to go for lightning nowcasting, all those things, your global model will not be helpful, because the resolution that global model take care of is 10 to 100 kilometer. However, your lightning or this one happens in meters. So that is why you will have to go for a regional or local model, because their resolution is 1 to 30 kilometer, and then your forecasts are reliable up to 3 days, and your forecast output you will get every 1 hour, and you can increase also, and the model runs every 1 to 6 hours. So that is why for your lightning forecast or thunderstorm forecast, you need to go for regional or local models. This I already said, your global model, it takes care of the entire globe and it does not take care of your vertical acceleration. And that is why the convection part you will not get from the global model. But for any lightning or thunderstorm, we need the convection, what is happening, that is responsible for the cloud formation. So you need to go for regional model. At NESAC, we are using the very famous weather research and forecasting model for our forecast part, because as I have already mentioned that here, as compared to the earlier MM5 model or ETA model, the numerical integration method used are very much accurate in compared to the earlier models, and it is hydrostatic and non-hydrostatic. That means it will take care of your convection. That is very important for thunderstorm initiation or lightning initiation. Then you can put nest, for example, if you want to run for the northeastern region, then inside the Indian domain you can put your another domain that I will come later on. And the design, the grid spacing is for about 1 to 10 kilometer. So WRF model we are using. Switch on the fan. And if you see globally how much the WRF model is people are using, mainly Asian countries, if you see, we almost everyone is using the WRF model. And why it is so popular? Because of its many advantages. Not only like it is numerically very stable, it is less time consuming also, and the model is very efficient and user friendly. You can make modifications based on the code available. So weather research forecast is globally used model or accepted model, you can say. In the weather research forecast model, mainly the components are, first, whatever data we get, all the data are not in the like model compatible format. We will have the terrestrial data, that is the surface observation, not observation, like terrain condition, land use, land cover data. So those information we will make it available to the model, and we need to either use the data from USGS what is available with the WRF itself, or we can feed our own land surface informations based on land use, land cover data or terrain data. Because I have already mentioned the terrain informations and land use, land cover information is very important for model accuracy point of view. And the gridded data, it either comes from GFS, we are using as of GFS, there are other sources also. Then these two data goes to the WPS, that is the WRF pre-processing. It first it combines the land surface data with the meteorological data and create the initial condition for running the model. Then these initial conditions, using some data assimilation module, we further improve, and then some post-processing tool like ARW post and NCL grades, we finally output the data which can be used by the users. Our WRF journey starts at NESAC in 2009. Just excuse me for a second, my door got open and it's great disturbance. Sorry for the inconvenience. Yeah, our NESAC, we have started in 2009, and since then we are doing lots of R&D so that we need not to like actually what it is, like IMD is already doing this numerical weather prediction for entire India. Then why we need to do separately for northeastern region? There are many such questions arises, but since 2009 we have configured the model in such a way that our accuracy of flood forecasting increases from mere 25% to now like 85%. Because whenever any synoptic kind of like a big event is there, then our model can 90% accurately it can predict. But whenever there are small isolated system, then model has some issues because it has resolution issues, then observation issues, lots of other problems are there. But when we call about a synoptic scale or big scale event, then our model can we are confident enough that okay, the model, whatever rainfall prediction it is giving, it will be well and good accurate. And for that we have started the model with just 27 kilometer, and now we are running the model at up to 3 kilometer resolution. And we have found out the differences also. While increasing the resolution, how it is helping. Then data assimilation. For data assimilation, there are different methodologies available, variational method, ensemble, Kalman filters. So these are different data assimilation methodologies we are using. And then for validation, validation is very important because when you run a model, whatever output you get, you cannot get convinced because it's kind of a Gogoi effect. Whatever input you will give, it will give you some output. So you cannot be blindly believe that, okay, if model is saying this much rainfall will happen, it will really happen. No, it is not like that. So you will have to do rigorous validation. So we do nowadays we do everyday basis, whatever rainfall forecast we give, we compare with AWS stations, GPM rainfall, inset rainfall, so that we can further increase the accuracy of the model. And here we have a 120 core HPC. It's not a HPC, but yeah, to some extent, 120 core machine. Currently, we are using at NESAC. And for data assimilation, we are using globally available data as of now, because AWS station data are not consistent. Because let me tell you here, when you go for using any observed data, the observed data quality need to be checked before you use in the model, because your model does not have any information about the error. So error information also you need to feed into the model. So you have to be very careful for operational purpose what observation data you are going to feed into the model. And as I have already mentioned, when you use a model in operational purpose, every day you are changing these observations, like whatever additional information apart from the global data, AWS station data, satellite data, these are the observation there you are every day changing. But what about the static observations or surface observations? Those observations we are not using, we are not changing. So that is why some R&D also required what kind of land use, land cover information or static information on terrain data. Those information also we need to use judicially into the model so that the accuracy of model increases. And apart from that, your as I already told, the schemes, parameterization scheme that is available in the model, how your parameterization schemes are performing, those also you need to check, because you cannot blindly go and use a model. There are n number of schemes are available. Scheme in the sense, for example, if I say for rainfall, there are two schemes in the WRF model, that is called the microphysics scheme and cumulus physics. Microphysics, it explicitly said every grid point how the cloud is forming, and cumulus physics is saying within the grid what is happening. For example, we are using a 9-kilometer grid. So your microphysics will say the cloud formation at the grid point explicitly. But what is happening inside the grid, this cloud formation, microphysics will not have any information on that. For that, you need a cumulus physics. And for representing these processes, your model will have n number of schemes. That is called as parameterization schemes. But which one is useful for your domain? So you will have to be very selective. So some R&D you will have to do if you go for running any model, that which scheme is suitable for your domain, because any model currently we are using are basically developed at US. So it represents the atmospheric condition there. But however, there are many schemes are developed, are available, which also represents the atmospheric conditions of our area. But how you will use, it's up to you. Because for example, in our place, we are using like Thomson-Groppel scheme for your, yes, this one, microphysics. So we have seen that the central northeastern part, the RMSE error is much reduced in compared to the Thomson, Better-Miller or KF schemes. So we currently stick to this because, but if you see, still there are lots of error over the Arunachal Pradesh towards the southern extremes, because with what data we are comparing, that is also very important. Here we are comparing with the GPM data, and GPM data, I mean GPM in the sense, this is the satellite rainfall observation, you can say. If you don't know about GPM, then it is a satellite observation of rainfall. And when we compare with that, over the terrains, hilly terrains, we see that GPM performance is very poor. So these errors, because of the GPM data or model, we cannot say. But we are mainly, what is more important for us is the Assam area and central Assam. We have seen errors has been reduced to a large extent with the Thomson-Groppel. So that is why we are using this scheme for our model. So my main message out of this slide is that not showing the research what we are doing, but the thing is like, when you go for an operational use of a model, what are the things you need to take care of? First of all, you need to see which physical parameterization scheme is suitable for your region. Then second is, the static data that you are using for representation of the surface, whether it is what is available with the WRF model, is it really sufficient or not? So if you see how our Earth surface is evolving, how it is changing, so the pattern of land cover and land use is changing every year. But whatever data available in the WRF model itself, it's a USGS 1992 data, very old data. However, our land surfaces changes a lot. That is why you will have to use the fresh land use land cover information, because finally your surface is interacting with your atmosphere. So whatever atmospheric condition you are providing, if you are not providing the land surface accurately, then your interaction will be poor, and then your representation or forecast of the rainfall will be affected. That is why you will also have to take care of the LULC data. These are some of the results to show when we use the ISRO land use land cover data, and this is the available WRF model itself has its own land use land cover data. Then we have seen that our rainfall prediction has been increased from 0.69 to 0.80. And if you see the biases, then probability of detection, all are improved when we use the land use land cover data, that is the updated data from NRSC. And like false alarm ratio also reduced while using this land use land cover data from NRSC. An equitable threat score means this scores, if it is higher end, that means your model is performing better. So that is way you can see the how a model depends on not only the atmospheric condition but on also the surface conditions. And this is the overall representation. Like there are two data available with the WRF model, USGS and then MODIS. Then this is the ISRO NRSC data, how the errors have been improved while we use like updated land use land cover data. Then comes your terrain data. Terrain data also, when we use CARTO DEM data, the underestimation that is observed with the USGS has been improved to a large extent. So message is, while using a model, you need to take care of the static data also. Then comes your data assimilation. I will not go to the technical part of it. I just want to show how the observations that we are using in the model and it is feeding into the model. See, n number of observed data. It's like observed data are in the power of 10 to the power 7. So this much observation data we are using to run a model. However, when we use the globally available data, this picture, if you see, this is the atmospheric motion vector. You see how many, what is the gap area here? Lots of gap area over the Indian continent. So how to gap fill this, and where comes the role of data assimilation? So our own inset, from inset data we get atmospheric motion vectors, and then when we just a second. Hello. Yeah, I'm a little busy. Can I talk to you later? I'm in a meeting. Okay. Yes, please. Sorry, there is another meeting. Okay. So how the observations are well distributed when we use the data assimilation methodology. So my message from this slide is, whatever global data we are using, we will also have to check whether this global data is really representing your area or not. If it is not representing, how to make it representative. For that, you have your own satellite data, then well and good, then you feed into the model, and then this lack of data, what is observed here, is how much reduced when you use your own satellite information. And then if you see this is to show how after using insert data, how the model performance is improving. That means it increasing the model accuracy. So this is another factor that you need to take care of. So when this is one incident that happened in Assam, then people died also within 1 hour of rainfall. However, our model could not capture this peak incident. This dot you have seen, there is more than 100 mm rainfall or 113 mm rainfall. That is not picked by our model, because we could not use AWS station data at that time, because the data quality we need to check for operational purpose. But after quality check, when we assimilate the AWS stations, we have seen that this how the prediction have improved to a large extent. That means, what is the importance of the in situ measurements in weather forecasting or any numerical modeling? we are like struggling with the observation network. We don't have sufficient AWS stations. Only we cannot depend on the satellite data, because during rainy season, your infrared satellite will not perform well. So it is the high time that we should have a dense network of AWS. Like if you see Karnataka, they have 7,000 AWS stations, but here we are struggling for AWS stations data. And because if you see, if we feed the model with good observations, your forecast skill will improve. So that is why we need to see the observations network, how it can be improved. And then this is one radar, DWR, that is here in Meghalaya at Cherrapunji, that after using the observations from the radar, our model forecast, how it is improved. Like the model, initially it is not showing any thunderstorm event, but assimilation or feeding the data from the radar, how it is representing the actual rainfall. That means how much it is improved. That means what is the benefit of this kind of dense observations. And then comes your multi-model or ensemble, whatever you say. Like in any single model, for example, if you run a single model deterministically or single one time, then your model will give you some forecast, but you will not know whether your forecast is this one, that one, which one. Anyone can be your forecast. So you don't know the whatever the error is involved in your model. But when we run multiple models, like for example, when we run the same model 50 times, then we have an estimation of the error, like how each member is deviating from the mean. So that means we are having that, okay, this ensemble is spreading away from the means it is having some issue. So that way we can correct the model, and finally another deterministic forecast can be given, which have information on the error involved in it. That's why that is called the ensemble forecast. So instead of using a single model, we are using multi-model, such that the forecast can be improved. These are some of the background work that we have done using the ensemble method or multi-model method, how the errors can be improved. I will not go in details. And this is what the flood early warning system, there we are, after so much of improvement into the model, finally this data goes to the hydrological model for flood inundation mapping. Under thunderstorm nowcasting, as you know, northeastern region is vulnerable to thunderstorm lightning. So this is an IMD map. You can see the number of thunderstorms happening over this region. So for that also we work, and using the WRM model and the data from other sources like INSAT observations, then DWR, then lightning. So those information we bring to a common platform, and then we give thunderstorm potential map. That means in the next 1 hour, which are the probable areas where the thunderstorms are likely to happen. So this is just a comparison with what we have predicted and what really happened. So for that also, we don't not only run the numerical weather prediction model, because as I have in the first beginning slide, I have mentioned that numerical weather prediction method have issues in the initial hours, like 0 to 6 hours. So for like filling that gap, we also need information from other sources. So combining all those informations from model, then ground observation, satellite data, we empirically develop some module, and that gives a thunderstorm potential map at every 1 hours. And then validation is very important, because without validation, you will not understand how your model is performing. We are continuously doing this effort. And then as I have already mentioned, how DWR data assimilation improved in the model forecast. Here also, if you see, after assimilation of the DWR data, your own observation, when you feed into the model, the thunderstorm event that is not picked by your model initially, it get picked up. So these are some of the things we should understand, that while we run a model, how observation plays a important role. So now comes the lightning part. In lightning also, the lightning potential map every 1 hour at NESAC we generate, and we feed the data that we get from IITM network. From IITM network, we get continuous lightning data, and those lightning data we feed into the model. And if you see the prediction given by, and then this is the observations. So it is how accurate it is. So up to say 3 hours, or mainly maximum, because it is a very localized, when lightnings are also not prevailing for long. So 1 hour forecast is very accurate, and after as time passes, the accuracy also decreases. For the like lightning forecast, we are using the WRF ELAC model. I will not go in details about it because Abhay will mainly speak on the lightning part. My duty is to show how numerical weather prediction is helping and what are the things that you need to take care of while you use a model for operationalize of anything. So here also lightning, we run the model at 3 kilometer resolution. Every 1 hour, the time integration, it happens, and then the forecast will be up to 48 hours. Here also data assimilation, mainly currently we are using the IITM data for assimilation, and then validation part. Validation, we are using ENTL and WLN, whatever data is available, if at all available, or otherwise data from IITM. Then other parameters apart from the this one lightning, we compare with AWS data, INSET 3D, GPM, then DWO data, because validation is very important. So these are some of the results that is showing how our predictions are to a large extent accurate. I will not go more details because I will not take Abhay's time, and I'm having another meeting and I'm getting called again and again. I'm extremely sorry for that. And finally, I just want to say that NWP is not a magic. Okay, if you think like if you give something into the model and you are getting the output, no, that is not correct. NWP is not a magic. So you will have to be very careful when you use a model. As from the beginning, I'm talking about the computational constraint. So if you want to make as somebody understand, like I want to run a model, I need this computational facility. So you will have you should have the complete understanding why you need, because the model computation, it involves more than 10 to the power 7 observation data, the equation integration. So all those things need a high-end computational system. Then your experience or alert forecast, because some of the areas now in Northeast, we know like if it is happening in that particular area, there must be some deviation from that area. So those kind of skill you need to develop with your understanding of your model, how it performs. Then the bias correction can be done. And then human skill is always there. Although you automate anything, finally it comes to the human skill. It means machine cannot replace human all the time. So your like expertise always come into picture. So while using any NWP model, numerical weather prediction model, for your forecast or for your operational work, you need to take care of all these things in the picture, like your observed data, your model errors, then your computational facilities. All these things plays a very important role, and we have struggled a lot, and now we come far. Like now we can say that okay, our models are performing well, and for at least for flood forecasting, what we have seen is the prediction skill have been improved to 85% or 90%, and it is really we are happy because we have started the work from scratch, like for a 10 core machine we have started, and now it is performing so well. For lightning also, we are the first organization, like as Kundu sir already mentioned, like we have assimilated the data. Even after that, IMD has adopted that. So we are happy that at least some contribution from our side, being a small center, we are also doing. May not be nationally, but regionally at least we are doing. This is our small team headed by Kundu sir, and we have like myself, then Aniket, Abhay, and one research scientist, Arundhati. So this is a small team. You can see in bigger centers, there are a lot of people, big machines, all those things, but we are a small center, less people, lots of responsibilities, but we are still doing research. Because why? We need to improve the forecast. We don't want to go for the gigo effect. No gigo, no garbage in, garbage out, because finally it is, you are helping the society, the grassroots level. Whatever you are in, your information is going, finally it is helping the public. So you will have to be very particular. Therefore we are doing a lot to in the research part, so that our model can be improved. With that, I will just say thank you, and thank you Srivastava sir for giving me the opportunity to present whatever work we have done in terms of numerical weather prediction for Northeastern region. Thank you, sir, and thank you all.
Thank you so much. In fact, very, very insightful. And you made presentation such a complicated thing so simple, you know. So
Thank you.
that's really very, very well done. And I can see because I have been interacting with NESAC, and it's a journey really satisfying journey, well covered, and the output, especially the flood, if you have gone to 90% accuracy, that's, too good. How much is your accuracy in lightning?
Sir, that I'll cover in my presentation. So lightning part I'll cover.
It's a surprise, it seems.
But I hope our interns have taken good note of it. Anybody, in fact, we have others also who have joined, like Dr. V.S. Prakash, founder director of Karnataka State Natural Disaster Monitoring Center. Then we have Professor Avdesh from Bareilly Adventist University, and then we have Mr. Srikanth. He's leading the Chennai bloggers, very important weather forecasters. So they all have also joined, and the number has also increased now. So students, any interns, any question you have? Lokesh, Pritam, anybody, any question? Prakash sir, any question? Any guidance, sir?
Yeah, it was a nice presentation,
Thank you, sir.
and I wish the entire group a lot of good work they have done, and a lot more they are prepared to do. I wish them all the best, and our support is always there with them.
Thank you. Srikanth, since you run a lot of model, may I request any input? Sorry, you joined slightly late, but
good afternoon. Thanks, Sudhirji. Actually, I wouldn't call it as a comment or something, but maybe a request from my side is that a couple of things which I have in mind. One is with a number of AI-based models developing, and including people like NVIDIA who are focusing on offering it as an open source thing. Would it be possible if, say, for example, something like NESAC would drive, because the biggest challenge for weather models in a tropical country like India is that we have factors that are much more complex compared to the temperate zones like US, and you always have this comment saying that in US people say it will rain at 3 o'clock, it will rain, it will stop at 4 o'clock, it will stop at 4 o'clock. India is not like that. I think with AI possibly with that allows better results with lower computing power. Maybe we should look at actively AI as one of the way forwards. One and two is this is possibly a question from my side. As Sudhirji pointed out, a lot of weather bloggers have observations over time. For example, when a model says that it might rain at a certain place or in certain condition, due to our past experience, sometimes we say it may rain, it may not rain, but that's purely based on whatever we observed. Is there a way to, for example, formalize it? Because I think that's a huge resource which might be a very good tool, because a lot of these documenting that the enthusiasts do over time can be a very good information in terms of sort of understanding model performance as well. Only these two things. Thanks, Abhay.
thank you. Any point, Professor Avdesh?
Yes, sir, it's a very pertinent presentation. I can see the forecasting can save a lot of life, and in this situation, we need more and more such type of technologies and their implementers. So I can see this. Second point, I think this is very important, that experienced and alert forecasters analysts may add on value to such numerical weather forecast. I think this must be, if integrated, it will come up with a great results in the such type of initiative. And a commendable presentation by ma'am. And this is all from my side for now, sir. Commendable one.
Thank you, sir.
In fact, we are trying to create a bloggers community in Northeast, let's
Right,
see.
sir. Right, sir.
so that the ground validation can be done. The connect is required from the
All
field
right, sir.
to this. But as far as the numerical weather prediction model is concerned, a very concise and very good presentation. And thank you, Dr. Rekha, for being there. I know you are holding from another meeting. So thank you very much.
Thank you, sir.
I'll share the detail with the students in case they want, they can interact with her later.
Anytime I'll be available.
Yeah. Now I hand it over to Dr. Abhay. Over to you.
Yeah, good afternoon, sir. So actually you have to make me host again. So I'll start the presentation directly.
Yeah, so the moment the presentation, I'll request Dr. Rekha. Yeah,
Yeah, I stop sharing.
now you can start. All, please switch on your video. I take it if you have not switched on your video, it means you're sleeping. Hope you are understanding something or everything went like a F-16 fighter. Zuck, over.
Sir, can you enable to share the screen?
Yeah, please go ahead. Sanskar, Amina, Ankita Julani, Farhana, please switch on your video.
Yeah, can you see it?
Yeah.
Yeah, good afternoon, everyone. So myself, Abhay Srivastava, and thank you, Rekha ma'am, for giving a detailed lecture about this numerical weather prediction that make my job little easy to explain direct applications of numerical weather predictions and other forecasting methods for the lightning itself. But before going to that, we have to little bit discuss about what is the lightning and how the instruments help us this lightning itself help us to detect them. There are some of the characteristics that helping us to know that where lightning is happening, and then by using various methodology, we can develop some forecast and utilize it for safety of general public. So thank you, Sanjay sir, for inviting us as a team to interact with multiple interns, which is from various background. So I'll try to make the presentation a little simpler, but it's still that is little bit science oriented. So if students have any question in between, they can drop the message, as well as in the last, they can ask the questions. So basically, once we say about the lightning, the few questions coming in our mind, that first thing is that how lightning, what is the lightning and how it is propagating, how it is initiating, the lightning and role of the atmosphere. Then is it possible to warn the lightning, or we can only see and then get stuck, get harm from the lightning? So these questions coming in our mind. So first thing is that we have to understand that what is the meaning of lightning. When we say lightning, the one thing is coming, lightning is basically understand first, it is a electrical discharge in 1752, and then in 1905, it is also get more explained that how it is initiated. Itself, we know multiple things, but still we are understanding lightning in a more detailed way. So first thing is that how lightning initiated and how our weather behaving. So I think first thing I have to cover it like global electrical circuit, and lightning is one of the part of the global electrical circuit. So basically, once you say global electrical circuit, basically we say till now you say that okay, temperature is increasing, or you say humidity is less, you say I am feeling cold because humidity temperature is less. So these kind of things we generally say. But one of the things that is missing, like any particle, if you are talking about the temperature, basically you are talking about the particles in the atmosphere. That particle get charged by different mechanism. These particles are getting some of the electrical charges. And how they are getting? By the rubbing, by interacting to each other, and then entire atmosphere itself is a cage of electricity. We can say, of course, we are standing on the ground of the ground of the surface. So basically, we are equipotential is 0 voltage, and if we'll increase our height, and if we are not touching ourselves from the ground, then by increasing the altitude, you can say our potential level will be 100 volt, 200 volt, 300 volt, 500 volt. Then it can go up to the ionosphere, and that potential reaches around 250 kilovolts. So if you are just increasing your height, your potential level will be increasing. Means you will be more charged. Like you see in the aeroplanes are more charged, and if you connect the aeroplane directly to the ground at any instant, that will be a discharge, and which will look like a lightning discharge. So you have to understand that is some breakdown is happening between cloud to ground and between the cloud due to these phenomena, which is difference of the equipotential level, which is getting connected by some mechanism. So I'll cover up that mechanism itself. So multiple phenomena is happening in the atmosphere itself, like cloud formation is happening. Charge of the corona discharge, small structures is there, and corona discharge is happening over there, as well as cosmic rays is coming from the various outside activities like solar flare and these things. Cosmic rays are coming, and they are also impacting the global electrical circuit. And then last thing is that thunderstorms itself. So thunderstorm is the source of the lightning, we generally understand, because the cloud formation and these things happens, and then charging mechanism get processed, and then discharge happens in the thunderstorm itself. So basically the discharge is, we say, lightning. So one thing is that when we say global electrical circuit, how we came to know that global electrical circuit is an important thing, and we have how it is linked with the lightning. So one thing is that once I am telling that multiple parameters which is impacting the global electrical circuit, one of the parameter is lightning. And once we are telling the lightning, you can see this picture, and you can see how lightning is happening in various part of the globe. So you can see in over the Asian region, over the African region, and over the American region, there is 3 regions where lightning is happening in different prospect. And then these light, if you go and see that when these lightning happens, so basically at any place, when you go local afternoon time, most of the places lightning is occurring. So one thing that happened in the earlier studies, that when we are talking about the atmospheric electricity, so multiple places people observe that atmospheric electric field, and that electric field is minimum around 4 UTC and maximum around 18 UTC, which is, we say, Carnegie curve. That is, you have to simply understand, Carnegie curve is a atmospheric electricity which is fair weather electricity. There is no lightning, nothing. But at the same time, what is happened, once this global lightning activities is observed by various methods, then it is found that around 6 UTC, the Asian and Australian belt is getting a highest number of lightning, and then later the lightning activities is get less. And then in African and European continent, the maximum lightning is happening around 12 UTC. And then on 18 UTC, it is on American zone. So 3 different zones. Once we averaged all the 3 different zones, that is looking similar to the Carnegie curve. So what this give the message that even though fair weather electric field is from 80 volt to 120 volts per meter, the lightning is directly contributing to maintain that electric field, because these peaks, once lightning activities are very low, the peaks fair weather electric field is getting low. When lightning peaks are at high level, the fair weather electric field is also getting high. So basically they are interrelated. So that's why global electricity is also coming in the picture before going for the lightning. So that basically interacted more of the researchers to understand how lightning behaving in the atmosphere. As well as you all know that climate change is happening and various parameters, various severe weathers are going to in increasing mode. And then lightning is one of that, which is we are experiencing that lightning is going to increase in near future, the number of lightning at a particular time period. So basically, what does that mean? We have to more careful for the warning, for the safety also. So two things which encourages the researcher to enter in the field, and more team is required, more manpower is required to do the lightning studies in this particular area. So basically, once I'm telling the thunderstorms is propagating lightning, basically thunderstorm itself is giving two kind of charging is happening in the thunderstorm. One is called the non-inductive charging and another is called the inductive charges. Once you are telling the thunderstorm, basically thunderstorm is the structure of graupel, ice crystals, and then rainfall. And these once these two different particles are coming closer to each other, one electron, you can see the picture one, magnified picture one, and then picture two and picture three. So you can see in this ice crystal and then hail are coming closer to each other. And in the non-inductive, what is happening? Basically, one electron is jumping to another particle. So in this particular time, the electron is jumping to another particle, and that is getting more charge, more negative charge. So basically, hail is getting more negative charge, and then this ice crystal is getting more positive charge. So that is the non-inductive charging mechanism. So another charging is the inductive charging mechanism. In the inductive charging mechanism, what is happening? Hail and ice crystal both are coming closer. And once you know that once, like if you rub your scale in your hair and taking a small pieces of paper and coming closer to that paper, your scale is coming closer to that paper, what will happen? That paper get interacted to the scale. Same thing is happening between the hail and ice crystal, and they are transferring the charge from one place to another place. So basically that is the inductive charging. So both is happening in the cloud itself. And then by these chargings, different kind of charge structure is created. So basically in general, we consider there is three type of charges is structure. Basically upper negative charge region, main positive charge region, and main negative charge region. So this is the main typical charge structure of the thunderstorm, but this is not the case at all the places at all the time. Sometimes it is dipole, sometimes it is inverted polarity. What is the meaning of inverted polarity? The lower positive charge region is much more higher, and upper negative charge region or middle negative charge region is basically very less. So then once this charge separation is created inside due to the graupel and ice crystals and hails, this charge structure is created. Then basically this charge structure is trying to accumulate more electric field. And once enough electric field is accumulated, that is making a discharge. And that discharge is happening either between the clouds or between the cloud to ground. So basically these are the lightning discharges. So if it is happening in the cloud to cloud, it is called cloud to cloud lightning or intra-cloud lightning. And if these discharges is coming cloud to ground, so that is cloud to ground lightning. So basically these are two basic categories of the lightning discharge. So once this lightning discharge is happening, multiple hazards are associated with that. That is, forest fire is happening with the lightning itself. Human injuries is happening, and public health is also getting damaged. Then industrial injuries is also happening. industrial losses is happening. And then final is that power grid is also get impact from the lightning discharge itself. So before going further, there is number of terms used in the lightning activities. And normally we, once as a student, we interchange these words very uncarefully. We change this word. So we have to much more careful about changing any word to another word to the scientific community, and that will helpful for you to explain your whatever the work you are doing in a proper way. So normally what is happening once this discharge starts, so this discharge is starting, you can see this right hand side picture, this discharge is starting by the leaders, which is basically in stepwise manner. These leaders are coming from clouds. So you can see this is the left hand side, you can see upper figure, step leaders are coming from the cloud, and these leaders are getting extended. And in these leaders, multiple branches is also happening. So after that, once these multiple branches is happening, one of the branch is getting a response from the ground, and these responses upward connecting leaders. Keep in mind that downward stepped leader is coming down, at the same time upward connecting leader is giving the response and trying to connect with the upward downward leader. So you can see in the right hand side picture, one leader is coming from downward and one leader is going upward. Basically it is taken from the high speed camera, images is there. So you can see, and then in the last moment they try to contact each other. Once they make the contact, so it is called the attachment, and all the current which is associated that started to flow. So this is called the return stroke. So you can say entire current is tried to neutral, but sometimes what is happening in a single return strokes, the current is not neutralized. Then in the same path, second return stroke is trying to accumulate. So basically the leader is again trying to follow the same path, and again second return stroke is happening. And in the same time, multiple return strokes can happen. And these return strokes is normally 40-50 millisecond time interval between 2 or 3 return strokes. So I'll come further in the examples. So once these return strokes is happening, multiple return strokes is happening, all together in 500 millisecond or 1 second, we say it a single flash. So keep in remember, return stroke is one thing, flash is another thing. So flash is the multiple return stroke can be together in a single flash. So there is two types of lightning, upward lightning and downward lightning. Both is, I'm just talking about the CG lightning. So upwards and downward basically told based on the whether downward leader is coming from the cloud towards the ground or upward leader is going from the ground towards the cloud. So which leader is started first and which leader is giving the response, based on that we decide whether it is upward lightning or downward lightning. So once this upward and downward lightning is decided, what charge is flown from the ground or from the clouds. Based on these charges, we say it positive cloud to ground lightning or negative cloud to ground lightning. If from the clouds, negative charges is coming downward, that means negative downward leader is coming down, and from the ground, upward positive leaders going upward. And this is the, because negative charges is coming down, that means negative CG. Similarly, if positive charges is coming from the clouds, so that is positive CG. Opposite, if negative charges is going upward and positive charges is giving the response from the cloud, that is called the upward negative CG. So keep in your mind that what is the positive and negative, what is the upward and downward light CGs. Basically, one more thing that started in the urbanization, due to the urbanization, which is upward lightning. Basically, upward lightning leaders from the multiple towers. You can see this example. There is multiple towers, and from multiple towers simultaneously, upward lightning is initiated. So basically, if you see the skyscrapers, we say that in urban area, lightning could be less because we are installing the protection systems. We are installing a proper safety tools, but still in that places lightning is also happening, and they are more vulnerable for the lightning. If proper protection systems is not installed, then a disaster will happen in the urban area. So to measure these lightning, we need various kind of instruments. So these instruments we need either for the safety, either for the observations. For the safety, we normally consider like protection system instruments, like Faraday cage, like air terminals, and many more. And in between, we also use power system protection systems. We use electronics protection systems. So various protection systems is available in the market, and you can simply ask to various organizations to help you for installation or for designing protection system. And Cropsy is also designing their own protection systems and helping to the villages to install the protection systems. And of course, the science behind all the protection systems is same, to pass the current in a lower conductive path. So whatever the current is coming from the lightning, you have to give a path which is lower conductive, lower resistive path. So basically is a highly conductor you have to use, like copper or something like that. So that conductor is helping you to pass the current. So then second type of instruments is coming, which is called the observational instrument. So basically one thing is that by the protection system, you are saving yourself from the lightning, but you cannot stop yourself to that place. You have to also try to understand the lightning, and for that observational instruments is required. So that gives us location, current, intensity, polarity, and these kind of things. So if you consider the lightning itself, we normally see some part of the lightning which is coming from the cloud towards the ground, and above the cloud there is multi more phenomena is happening, which is called the blue jets, which is called the TLEs. And these phenomena all together, what is happening once I say the lightning, basically that is the light, and light is the electromagnetic signals. And so once we are saying the EM signals, they have some frequency, and these frequency in the lightning, basically once lightning happens, they are from VLF to VHF. All the frequencies are radiated from the lightning. So lightning itself is an optical event, but this lightning it's radiating very low frequency, very high frequency. And these frequencies and together with other phenomena like lightning is generating the sound, lightning is optical observations. So these together, we can utilize these particular characteristics of the lightning to observe them. So to observing them, optical observations can be happen. So high speed camera or normal speed camera is used. For the electromagnetic signals, we detect the lightning, and electromagnetic sensors like Earth Network and various ILDN and other IITM Pune, they designed their own sensors, and these sensors can help you to detect the lightning, electromagnetic signals basically. And then electric field detection from the lightning is also possible. And in the last, optical observations can be happened from the ground, as the same thing can be happened from the cloud itself. We can also utilize the electromagnetic signals from the cloud also. But till now, I don't have any example which is using satellite to observe the lightning using the electromagnetic detections. Normally, we are using the optical characteristics of the lightning to detect the lightning from the satellites. So if you say the lightning, so as I told you in the beginning, lightning is happening in the cloud and it is coming towards the ground. So if the lightning channel is coming from clouds towards the ground, basically at downward movement, very high frequency electromagnetic signals are radiated. And once return stroke is going up, very low frequency signals are radiated. So for mapping and for other purpose, very high frequency signals can be used to understand how lightning propagated, how step leader is behaving, how thunderstorm microphysics and electrical behavior is working. And then for the warning systems also. Then VLF signals, which is radiating during the return strokes, can be utilized for the warning systems, for severe weather understandings, and for other principles. So basically, once I say the BHF signals cannot go far, means they are limited at a particular boundary, where LF signals can go beyond that boundary, and VLF signals are much more beyond that boundary. So like that, these signals propagate. So like I say, if a very old person is there, he can travel 10 kilometers, then young man can travel around 20 kilometers, and then a child can travel around 30 kilometers. So like that, you can relate with VHF, LF, and VLF. So this is one of the instrument which is called the atmospheric electric field measurement. So this instrument is utilized to understand what is the electric field in the fair weathers. So normally I was telling about the Carnage curve. So this is basically a fair weather electric field which is lies between the 100-120 volts per meter. But once lightning is happening, that is called the disturbed weather, the electric field reaches around 7,000 or 8,000 volts per meter. So in that case, if I say the fair weather, in general, you can calculate by Gaussian law itself. Like if someone of you are from the electronics or physics background, you can simply use this equation and consider the radius of Earth is 6,400 kilometers, and then Earth surface charge accumulated is 100 kilocoulomb. Then what could be the electric field? Normally, it is 120 volts per meter in the fair weather. So then, as we understand different kind of mechanisms to detect the lightning, so what are the methods to estimate the lightning? There is magnetic direction finder, and second is the time of arrival methods. So what is the magnetic directional finder? Basically, we use two kind of loop antenna. We install the loop antenna at different places. As the example I already given the loop antenna. So there is one loop is from east-west side and another loop is from north-south side. So once lightning is occurred, that will radiate the signals, and at a time like 30, 40 or 50 milliseconds, these signals will receive this lightning. Like you heard that sun is starting to rising at a particular time, and after 8 minutes, it is reaching to the ground. Means it is taking 8 minutes to rise the sun. Similarly, if lightning is happening, suppose in Delhi, it will take around few milliseconds to reach in northeastern region. So this time delay is basically utilized to understand where lightning is occurred. So what we do, we install different antenna, and from different antenna, we just see that where is the east-west loop is where peak is coming, and where north-south loop peak is coming. And then we calculate that peak difference, and that is called the direction finding. So basically, we use this formula theta, where theta is this, and then V out in north-south direction and V out east-west direction. The division of tan inverse is basically the direction finding method. Then another method is called the time of arrival. What time of arrival method? So basically, once lightning has happened, two kind of signals are radiated, and once these antenna, which I told you that the electromagnetic receivers, these antenna receive the signals, and once the return stroke is there, you can see this particular picture. The return stroke is basically very sharp decay and slowly increase. So this particular peak is find out. You can see 270.95 millisecond. It is find out. Then another peak is by the distance and by the distance of the particular sensor. These peaks are coming at different places. And then these are the examples of various return strokes that is happened in a single flash. So you can see in this first signal, there is 1, 2, 3, 4 return strokes is happening. And how these return stroke is looking? This is the first return stroke, this is the second return stroke, third return stroke, and this is the fourth return stroke. So in a single flash, in this observation, 4 return strokes is observed. So suppose at one station, if we are, you see the lower figure, if one station, we received a return stroke and the peak is going like this. This is the peak. This is the peak. This is the peak. So you can see there is what is the distance? 122 kilometers. Then second station is suppose available at 85 kilometer. The peak is this. So basically, you can see this is the peak and the associated peak is this. And in some stations, maybe peak is not at the same places. So basically what we do, we find out the particular peak point and finding by the cross correlation, we relate, okay, this is the peak from the same return stroke. Basically this peak which I am telling. So it is coming from the same return strokes. And when this return strokes happen at location 1, location 2, location 3, location 4, location 5. Basically, what is this location? This is the places of X, Y, Z, and T. You know the location of sensor 1, you know the location of sensor 2, you know the location of sensor 3, you know the location of sensor 4. And suppose this lightning happened on this place, it will start radiating, it will start radiating, it will start radiating in all the locations. So this location will receive at a particular time, this location will receive at a particular time. So basically all the sensors will receive at different times. So what will be there? There will be 4 different X, Y, Z, which we know, and 1 X, Y, Z, and T, which we don't know. So if we have 4 different equations and 4 variables, what is that? We can easily solve these equations by simple algebraic method. And after solving, we can say, okay, this is the particular lightning event, which is occurred in the particular location. So then if you consider the global scenario, there is number of lightning sensors is available, like Earth Network, like GLD 360, like WWLLN. And in regional basis, in India itself, there is 2 lightning networks working at present in low frequency. One of the network I did not mention here, but that is also working with Tripura University. So NRSC lightning detection sensors is there, then IITM lightning detection network is there. So these networks are helping to get the lightning at every minute or every second in the entire India or nearby region. So what is that? This is the example of lightning sensors. You can see these are the places where lightning sensors are installed. In India also, there is one sensor installed around the Tripura. And every year they are trying to increase the number of sensors. Sometimes they also install in this Pune area. And some of the sensor, if not working, recently Bangladesh also installed a sensor. So like that, it is happening to entire globe. So then what they are giving? They are basically giving what is the lightning H every 6 hours. They are updating this particular figure. How many lightnings is happening? You can go to this WWLLN website and directly get the lightning activities, and there you can understand more. And these data you can also try to download. There is some code to download this picture, and then another code is that to extract the lightning information from this picture. So you can freely get the lightning data without any limitations. So you can try. So in India, there is number of lightning sensors installed, and these sensors are working in time of arrival method. They are giving 2D and 3D method, and basically the type of lightning, that is CG and IC, both are given by the Indian Lightning Detection Network. So if you try to evaluate the lightning network, one of the things, once you are telling we developed a lightning location network, and by using different algorithm, you are trying to locate the lightning. So one of the things is coming in the picture, how to validate. So basically one of the validation method is that to find out number of shared lightning activities. Like suppose you have network A and you have network B. From network A, like network A, you can suppose sensors from ISRO. Network B, you can suppose the network from MOES. So you can find out how many lightning activities are located by both of the network. Then what is the spatial difference and what is the temporal difference between these networks about the location, about the time? Then you can simply say that this is the relative detection efficiency or relative detection accuracy, and performance validation can be done at some extent. But the best method to do any kind of performance evaluation, you have to use some another remote sensing tool. Like for validation, of location network, you have to use some other kind of like radar. You can use high-speed video cameras to validate the lightning location network. So for detection of the satellite, for the satellites, what is happening? Basically, satellite captures the image of the from the cloud. So all the optical, you can see this is the optical images captured, and from these optical images, basically this try to differentiate all the arrays which is found over there. And if these are the different arrays, once they try to convert it in the binary, and then they say that, okay, these are the arrays are connected and there is no connection, then again these are connected and there is no connection here, and then these are the connected. So basically this is separate, this is separate, and this is separate, and these are the separate events. So all together this is a single flash, but different events is happening. So what is the events? Either step leader or return strokes or a dart leader or subsequent return strokes is happening in a single flash. So a single flash can be multiple events, and in various events, maybe from the satellites, all the things will not be visible. Some of the part will be visible, and like that, we say, okay, these are the events is happening in a single place. So if you see the global scenario, there is TRIM LIS is available. Then LIS International Space Station is also available. This satellite sensor, the data is freely available. Unfortunately, till at present, December 2023, these data is stopped. International Space Station removed the lightning sensor, so we don't have any coverage of lightning from the satellite over the India. But at the same time, other places of the globe, they already installed the lightning sensor in another satellite, like European and American countries, they installed in the GOES, and then China is also installing F54A. So F54A, some part of Northeast is also covered by the F54A sensors. So this is basically simple example. In a one day, how many rounds this International Space Station was covering, but as it is not available, no need to discuss. So basically, this is the common detection frequency of the lightning. So you can see this is the density, which already discussed in the beginning. So these are the, even though you are changing the sensors, you are changing the location methodology. From each of them, we are finding basically three basic chimneys is available in the globe. One is the Asian chimney, another is the African chimney, and third is the American chimneys. So these chimneys are available for the lightning. So there is number of limitations about the lightning in India. So until now, we don't have any geostationary satellites. In India, one of the major things that need to be completed, that is validation and performance assessment of both of the network, which is I discussed today. So one of the things that we are doing in Northeastern region from these data sets and from these understandings from the lightning, first thing is that lightning, we developed a lightning alert system. In this lightning alert system, we developed a tracking methodology and a modeling methodology. As ma'am already explained you what is the modeling methodology. So I'm not going in detail about the methodology, but I'll show the results directly to you. So basically what is happening, we are using WRF elect model, and in which these are the initial conditions we are giving. And then we are assimilating the lightning data. Lightning data from where we are getting? From this zone. We are directly getting the lightning data and we are assimilating it over there. And then we are generating the probability of lightning. And this probability is basically 1 hour, 3 hour, 4 hour, 5 hours, or 6 hours, up to 9 hour lead time, we are generating this probability. At the same time, we are also validating the lightning. And you can see this is the forecasted. And after that, we also validated this is the correct forecast. You can see. And then second part, what we are doing, at the same time, we are converting these lightning in a density, spatial density map, and locating the active lightning zones where this lightning is happening and obtaining the cell from that. And then from this, we are predicting the lightning, where lightning is going to happen. So the accuracy and these things, I'll come in next slides. So basically domain is already, we have 3 domain, ma'am is already discussed it. So here you can see this is the forecasted lightning activity, and then what lightning we observed. So you can see these are the exactly observed and forecasted are observation and forecast are very similar. Only difference is that the categorization. So categorization means either we are overestimating or the entire lightning activities is not captured by the location methodology itself. Similarly, here is also say lightning is forecasted and here lightning is observed. So location wise, the accuracy is very high. And then we can say by this example, what is the accuracy and these from the temporal basis. So you can see there is 1, 2, 3, 4, 5, 6. Basically, these are the lead times. So if I consider the lead time of 1 hour, that is more than 80% accuracy, and lead time of 4 hours, the accuracy goes around 60 to 70%. So means up to 4 to 5 hour lead time, we can utilize this WRF elect model to forecast the lightning over the region as well as for entire area. And these lightning, after forecasting, we are also simply updating this forecast to this particular website, and every day we are updating this website based on whatever the forecast we are generating. So once this forecast is generated, this will give you the overall pictures. Okay, these are the patches where lightning is going to happen. But still, this is not the case in the reality. Reality, what is happening? In a small zone, thunderstorms is coming, lightning is happening, farmers is going to work, and we cannot stop them for entire day or entire time. You can not work today to the field. Then we worked further and started to track the thunderstorm using the lightning data itself. So suppose thunderstorms is here, and basically this is the danger zone area, and it is supposed to propagate on this place after 10 to 15 or up to 45 minutes. So basically we generate an alert on this area. This is called the alert issue, and stay in safe places. So this work is already available in the websites. And then this validation is also done. And you can see what is happening. We are getting the data from the northeastern region, and then we are transferring, converting them, and then this entire thing is generated, as I already explained them. So at present, what is there? This is a kind of tracking system, which is GIS platform, on the GIS platform, and all the storm cells are tracked very correctly. And then where this thunderstorm is going to happen, we can propagate. So you can see this is our dashboard. In this dashboard, these are different kind of thunderstorms which is going to propagate. These are different colors are passed to present lightning. Present lightning is in the red color. And you see how thunderstorms is moving and how it is forecasting. So this pink color polygon, basically, we are generating this forecast on this places. So alert is also getting generated. So basically, these are the polygons which is utilized to generate the alert. So this is the real time. What is the latency? That is the only 5 minutes delay is happening for entire process. So even lightnings happen, we are capturing that one, and then according to that we are forecasting. So we are getting a 45 minutes lead time to forecast this kind of lightning. And then the accuracy, most of the time it goes above 80-85%. But sometimes due to internet failure, due to power issues, due to other issues, we feel that, okay, this time lightning is why it's happening, and we were unable to forecast that. That is happening in this. So in this, this particular thing can be seen in our website, NER region. And in this website, we refresh this particular forecast every 5 minutes. So you can see the updated forecast. And then also we are generating the lightning reports every day. So you can utilize this lightning report to understand how much lightning has happened over the northeastern region. So these reports can be also utilized. And then third thing is that even though we are concerned about the farmers, even though we are concerned about the people who is working in the field, one of the things is also coming in the picture. If suppose we are going to organize some events, or we are going to design some small kind of activity, for that, whether we can forecast the lightning. Yes, very small, very simple instrument is coming. that is standalone fixed point instrument, which is called the electric field meter. So this instrument is basically what is giving. This instrument is giving the electric field. So once lightning is even happening 50 kilometers away from your location, this electric field is going upward, which is increasing like 1000 volts, 2000 volts per meter. So once this is coming overhead, this reaches around 5000 or 6000 volts per meter. But this can indicate that, okay, lightning is going to occur and thunderstorm is approaching to you, and you can be go in the safe places for time being once electric field is going to increase. So various method is utilized for that. As one of the method is probabilistic method that I used in a few years back, and then similar method we are trying to develop over this northeastern region. And then one of the thing that lightning is not happening at the same pace, same density manner at every places. The population is not same at all places. So which place we have to take more precaution measures to save the for the safety. Basically, for that, we need to understand the hazards of the lightning, where lightning happens more. So basically, from the LIS sensors data, we generated the hazard map, and we found that these are the places, small places where lightning is happening more. And these are the places where lightning is not even occur in a single time. So like that, we are increasing the resolution, and after increasing the resolution, we can even go to the district level like Kokrajhar and Dhubri districts, like here Karimganj district and few districts of Meghalaya here, which is getting more lightning activities. So once these are the case, we can our another team, which is called the HRVA team, urban division, that what they do, they utilize this information, and by utilizing the local population, by utilizing the number of houses, concrete houses, number of kacha houses, they try to generate the hazard vulnerability and risk assessment. So there are a number of applications about the lightning forecasting, like regional meteorological agencies, aviation sectors, and air traffic controllers. They can utilize this activity, this particular, whatever the forecast we are giving. Even though whatever the forecast we are giving, what we did in the last month, whatever the forecast polygon is there, we simply send this to the regional officers, and then revenue officers, they know that, okay, within a 45 minutes or 50 minutes, lightning is going to happen in a particular area. So what we learned today, in summary, I can say atmospheric electricity we discussed, thunderstorm electrification, charge structures of the thunderstorm. We discussed about the lightning physics, propagation mechanism, type of lightning, etc. Ground and space-borne lightning detection instruments, working principle, signal processing, and validation methods. We discussed about this one also. And then limitation, applications, and nowcasting of lightning to reduce the risk in a present scenario. So these things we have discussed today. So I hope these entire things help you to understand what is the lightning and how we can reach up to the last mile to save the people from the lightning by utilizing the lightning as an information, by utilizing the lightning as a tool itself. Okay, thank you so much. These are some books which you can utilize for your further knowledge, or you can also write me if you need some of the information. So can you say what is next in atmospheric electricity and lightning? Over to you, sir, and over to students. Thank you. Okay. So I think students then ask the question if hello, sir. So over to you. And students can ask the question if they have any questions regarding the lightning and these whatever the activities I explained, and even whatever the Rekha ma'am explained. If you have any question, you can ask from the today's all the lectures. You can ask the questions. or
Thank you very
any
much.
suggestion?
Thank you very much, Dr. Abhay.
Thank you, sir.
A very, very detailed presentation. You see everything from minute point of view, how the lightning forms, how it is in the sky, how is the leader, the return stroke. So it's a very, very really enlightening presentation because it will make you understand how lightning evolves. And you already had a earlier session from Dr. Trishanu Banik on global electron circuit, so you are aware how it functions. So you have got a holistic, presentation on lightning. Anybody, any question, please open up. If no question, या तो कुछ नहीं समझ में आया, या सब समझ में आ गया.
Dr. Sanjay ji, with your permission, I'll make a suggestion to Dr. Abhay.
Yeah, thank you.
Dr. Abhay, of course, my knowledge is very limited in terms of tracking lightning, but I've shared a few instances with Sanjay ji as well. I use a site called Meteorologics where you can also know the intensity of the ground strike. It's given in kiloampere, basically. Okay. So a few years back, 2-3 years back, on an average, mostly the strongest strikes would be around 110, 115, or maybe 100, up to say 150 kiloamperes.
Okay.
But for the past year or so, we are also seeing strikes as high as 330, 350. In a couple of instances, we've seen almost 450 kiloampere strikes, ground strikes. Right now, this is something which is very dangerous because if assuming the ground strike intensities are increasing, I don't know whether is there a trend to it or not. Possibly we may have to study that because if the ground strike intensities are increasing, then the risk is exponentially increasing as well.
Yes.
So is there a way that this could be possibly studied? And of course, then the next question would come is what is causing the increase in intensity of lightnings? Of course.
Okay. So I'll answer your second question first, and then first question secondly. That first thing is that we all are aware that temperature is increasing at present. There is no doubt. Climate is changing. Temperature is increasing day by day. Means respective temperature, average temperature is increasing. That we know. Even our summer is much more hotter. Winter is even getting less colder. So these things is happening. And these temperatures is helping us to form the thunderstorms itself. So for forming the thunderstorm, higher temperature with humidity. So our region is coming near to three side. It is from oceanic side. So basically this is giving us more moisture. So moisture is there and then temperature is going to high. Then of course thunderstorm formation, convection will increase. And once convection is increasing, the lightning means inside this thunderstorms, charging mechanism will change. And this charging is happening more and more, stronger electric field accumulating inside the thunderstorms. And then the third thing is coming, the lightning. Then of course, if thunderstorms are increasing day by day, then lightning will increase because these are the directly proportional to each other. So convection is increasing due to the increase of temperature, and that's why lightning is also increasing at South Asian region. You cannot say all over the globe at the same statement is not applicable at all over the globe, but in the South Asian region, South Asian countries basically, they are experiencing increasing trend of lightning that we all know from various studies is already available in the literature. Then second question is coming, the current. Actually, if you say about the urbanization is what is happening day by day. This high towers is making, skyscrapers we are making, and this skyscrapers and towers, they are basically responsible for upward positive lightning. So you have to understand that one of the categories lightning that is happening only on the very high structures, like 120 meters, 150 meters, or 200 meters. So these skyscrapers are getting more upward positive lightning, and the positive lightning current are much more higher in compared to the negative lightning. So for the general public, if you consider, if you pass 10 kiloampere current, that is still harmful. 300, 400 kiloampere is beyond our limit. But if you consider like 10 ampere or 20 ampere passing to our body, it is harmful to us. So loss will happen. Even though we are recording the number very high current, that is due to the skyscrapers, they have their own protection mechanism. So they are not much more harmful. If we simply remove the urban areas, then of course it is possible, but which is out of our limit. So we cannot limit this higher intense lightning activities. And then the frequency of the lightning, like number of intensity of the lightning is increasing. That I agree totally with you. The reason I already told. And just this is all. I think this is.
Yeah, thanks, Dr. Abhay.
Welcome.
In fact, there is a conference going on in Delhi, International Conference on Power Sector Resilience by CDRI.
Okay.
Yeah. Today only I have sent a note, the impact of rise in the atmospheric surge on the power sector, because it is right from the power generation, transmission, load management, distribution to the consumption level. The phenomenal rise in the atmospheric electricity is impacting.
Yes.
At the same time, India is on a path, or the world is on a path to a renewable energy adoption. And from the traditional electric field, that is the hydroelectric or grid charge, or the coal-based or thermal power plant, we are shifting to the solar, we are shifting to the other sources of power, wind energy. So these surges are going to affect all these, especially the solar panels. They are, since they're large, exposed, so they have a more threat than other things. Like we are floating solar charge. So since they are above the water body, so that gives a more attraction to the atmospheric surge. Similarly, the wind energy. We saw the wind energy with the heat and thunderstorm melting, So there are various types. You may add, Dr. Abhay, more, but I personally feel that we really need to incorporate lightning protection in these. One of the remedial measures suggested is go for a underground transmission system. Underground transmission system, up to some extent, yes, it will give protection. It will have reduce the exposure to the atmospheric surge. But there will always be a point where there will be exposed part, and again, once the distribution comes, it will be exposed. So those points are highly vulnerable, because
yes, if it is not planned in a proper way, like at present, whatever the wind mills we are installing in Gujarat, where thunderstorms is very rare. If we are going to install wind mills and these things in the belt of Bay of Bengal, like West Bengal, even any place of the eastern side, that will be a disaster for us. And if we are going to the western side of our country, that will be, even though that is outdoor, only 1 or 2 thunderstorms and lightning activities is happening in compared to the northern side. So these things, like once you are trying to develop some kind of infrastructure, the protection measures, as you mentioned, that one of the things is that to understand the hazards map, where more hazards things is happening, and then this planning should be happen. So proper understanding of hazard map is required before planning anything related to the infrastructure that will helpful for the development of the entire country. I can say like that.
Anybody, any question? If there is no question, then I would like to do a concluding remark that a very good session, especially two aspects of lightning, the WRF model, which has been shown to you. So that's a exposure, new exposure to you, and the lightning in detail. So far, nobody had told you in so much of detail, and a lot of effort taken by NESAC in designing the presentation. So thank you, Dr. S.S. Kundu, Dr. Rekha, and Dr. Abhay. Dr. Kundu, anything would you like to say?
Yeah. Yeah, I think happy to note that the presentations were useful to the presenters, and I think we got a couple of feedback also from Avdesh ji and others. So this will definitely help us, as we are aware that we are trying to give some of the forecast on an experimental basis, because we are not mandated to give forecast, but it's Northeast region. We have a node called Northeastern Regional Node for Disaster Risk Reduction. And under that, we have been trying to make use of the space technology as much as possible to provide disaster management support to the Northeastern states. And under that only, some of the disasters that are of major concern to Northeast region, we have been working, and lightning is one of them. So I once again thank you, Sanjay Srivastava sir, for the opportunity, and looking forward that in the future also we'll have similar opportunities, and we'll have you. I'm looking forward to have you here at NESAC sometime, and for some activities related to lightning. So thank you, and I also thank both of my colleagues, Dr. Rekha, Gogoi, and Abhay, for agreeing to deliver the talks. Thank you, sir.
Thank you, sir.
Very nice session. And with the permission from NESAC, we will close the session. So we declare the session closed here. Thank
Thank
you.
you.
Thank you.
Thanks, Sanjay.
Thank you, sir.
Thank you.